Hello, it's me, and I thought I'd give an example of how to approach increasing levels of complexities in a puzzle. What do I mean by that? Well, I'm going to start off with one type of complexity, which is just this pentahedral puzzle. This is what's called a standard pentahedral, three-layer version of this, and it's really it's a cute little puzzle and a quick little solve, but I thought I'd give an example of how to kind of expand strategies as the puzzles get more and more complex. So we're going to start off with this guy. So this is almost like a domino in that it only makes 180-degree turns in this plane, but you can make, well, 120-degree turns in this plane over here. I think it's 120. Who knows? What am I, a mathematician? Anyway, so what I'm going to do is scramble this up and just show a quick solve with this. So to scramble, I'm just going to turn this over here. So you can see that the movement is fairly limited. So looking at this, you realize that it's not a very complex kind of a solve and not a very complex scramble. So I'm going to keep doing this. Abracadabra. Okay. So it's a limited scramble for a limited complexity of a puzzle, but we'll just get started with this. So the first step to do is to understand that the middle layer doesn't scramble with any other layers. Only these two layers scramble with each other, which means that this one is something that just scrambles with itself. So all we have to do is do the right turns and positionings to bring this in, because it's not really scrambled with anything else. The limitations of the puzzle is it moves just like a cuboid, just like a domino, where you can't do a 90-degree turn here, you can only do a 180-degree turn. Here you can do your, in this case, 120-degree turns. So what we're going to do is we're just going to position these. So what belongs here? Well, this one does. So the easiest thing in the world is just move it in. Bang, there it is. Once this is all lined up, all we have to do is turn it once, and now this is all in. And it is as simple as that. So that's pretty easy to just kind of put in intuitively. The next step is to place the top and the bottom. So this is the purple top rather, because it's got a purple center here. I'm going to put the edges in first. This is the blue edge. Just place this over here. Now what you want to do is you want to put the purple edges from here up to the top. So this one has an orange one. So to put it in, just put it off to the side. We don't want to mess up the middle, of course. So we take this, move it down, pop this in, snap that right up into here. So basically this is now in. To put this one in, same thing. This is moved to the side, turn it down, put it in, snap it back up. So all these are in. To place the corners, this is done with exactly the same method as cuboid strategy, or as actually any cube strategy, where you're doing a corner switch from top to bottom. So you see blue and orange here. Move this above the blue and orange on the bottom where it's supposed to go, and then just do the algorithm. If this is R and this is U, and this is not a new algorithm, we've used this before, 2R, U, 2R, UI, 2R. So that places this here. Now notice we ended up with misplacement of this layer here too. Well, that's not really a problem. All we have to do is continue to move our R's in this position, because the next time we do that move, it'll put this back in. So we have this one set up here, orange and white. So find the orange and white right over here and do the same move. 2R, U, 2R, UI, 2R. This is in and this is back. Now we have one more to go. So it'll be the easiest thing in the world to do the same algorithm to put this in. The problem is we're going to end up with placement if we do that. This will be solved, but we'll end up with misplacement here. So what we want to do is put a dummy one in here first so that we can get the misplacement, then put this one in to get the misplacement out. So what I mean by that is move this to the side, go ahead and put this one in down here. 2R, U, 2R, UI, 2R. So what that does is it creates the misplacement here now, so that when I finally move this in, it'll fix this and put this in. So 2R, U, 2R, UI, 2R. So that managed to put the bottom one here. And this top just got solved. Now, I've redone this tutorial 3 times. And every time, this ended up magically solved. So if I were to have solved this right out of the box 3 times, this would automatically get solved just by solving the bottom. I know that to not be the case, but I kept stopping it, restarting it, and doing it over again because it got fixed. This is a super easy puzzle, and it'll solve itself if you just stare at it long enough. But let's say the top actually was a little bit more challenging. Here's what it might look like instead. Okay, now you might actually have a scramble where it does this, as opposed to every time I scrambled it, where it never happened. But anyway, if this happens, then how do we move these guys? What do we do to move this? Do I need to invent a new algorithm? And the answer is, fortunately, no. Instead, I'm going to use an old algorithm in a completely different way, for a completely different purpose, but the motions are exactly the same. What is that old algorithm? Well, I'll demonstrate it quickly here on my mix-up puzzle. I'm just going to use it as a 3x3. But you're going to do a corner swap. 2R U, 2R UI, 2R UI D, 2R UI, 2R U, 2R. Move this back. It swaps these two corners. Forget about what it does here, but it swaps these corners over here. It also swapped these two edges. So that algorithm, we'll swap it back. Turns out it does something very different here. Now, people have asked me how I come up with algorithms, how do I figure things out. Well, to be honest with you, the first thing that I do is I try to take an algorithm that I know and just apply it to this puzzle and see what happens. Because of the different pieces and the different shapes, it can have very different effects on the puzzle, but an algorithm is an algorithm. A commutator is a commutator, and if you do it right, it'll return you back to a position of unchanged position of other layers and move these layers around. So what that same algorithm does, the same algorithm with this, is it actually keeps the corners fine. Because when you're doing that motion, 2RU, 2RUI, here you don't overlap certain corners. Here you do. So the only thing that you're going to cause a change in is the edges. Now remember, if we were just focused on the edges, that algorithm swapped these two edges over here. These two swapped. If you didn't care about the corners and you just cared about the edges, that would be an edge swapping algorithm as opposed to a corner swapping algorithm. I use this concept with certain bandage puzzles also to get the other, what I call minor effects of the algorithm as opposed to the major effects that I usually use. So with that, I'm going to take that same algorithm and use this as a minor effect, becoming a major effect for what it's going to do with these. And because you have these guys that kind of overlap, more so than in a cube, you're going to cause a shifting of all three of these edges, and that's really what we want. So what's going to happen with that same algorithm is all of these are going to rotate clockwise. So we're going to do 2R U, 2R UI, 2R, UI D, 2R UI, 2R U, 2R, and this rotates back. Now, although it's not solved, what did happen is this did rotate. The blue one was here, and now it's here. So if we do that algorithm once more, then the orange one will come here, the white one will come here, and the blue one will come here. So that algorithm will cause these edges to rotate clockwise. Now you could do the inverse of this algorithm by starting with an L and do a 2L UI, 2L U, 2L, and then do a U DI, and then do a 2L U, 2L, UI, 2L. So anyway, just take what you did and inverse it, and you'll cause it to go the other way. But for ease of description, then I'm just going to do it twice. So 2R U, 2R UI, 2R UI DI, 2R UI, 2R U, 2R. It'll shift it, and it'll be done. So what I did is took the same algorithm that I would use for a 3x3, having a known effect that it's going to have with edges, realize that it's not going to have the same effect on the corners, and also realizing that you're really not going to scramble these. You're not going to end up with two that are swapped. I know that that goes against the parity of this puzzle, and there's no way that I'm going to scramble this puzzle to make that happen. So it's always going to be lined up no matter what I do. So I knew the algorithm, if it was going to change anything, it was going to change the edges. And because there's three of these edges, there's no way it was only going to change two. It was going to change all of them. So that's basically what led to that. So what if we were to take this and put an extra layer on it, such as this? Could I solve it the same way? And the answer is sure. Why not? Because basically what this is they put a circle here and they allowed it to spin on its axis over here. So the overall strategy is just like I had a middle layer here and a top and a bottom. So too I'm going to have a top and a bottom. The middle layer is going to be this whole thing. So I'm going to solve it the same way, but end up with this over here. So do I even need to go through the strategy in order to show that? And the answer is yeah, because it's not quite as simple and there is a little bit of a sticky point. So how can I take this? We'll go up the next level on the complexity ladder to this guy. So a neat little puzzle. We'll go ahead and just make some scrambling motions here. Just show the motion of it in case you guys don't have this puzzle yet. Okay, abracadabra. Okay, so now what I'm going to do is start the same way. Just like with this, I'm going to get the middle layer in. So how am I going to do that? Well, I've got a white one here. Where's the other white one? It's here. So obviously this has to be flipped somehow, but there's no way to flip it easily because, well, the middle layer doesn't really scramble like that. So I'm just going to move it away from here. And I'm going to move this across here, which will put this opposite here. So now this can move into here, put it in, and it's done. Again, this is the easy step. So now we just do the top and the bottom. Now here's a key difference that you may have, well, keyed into. With here, when I did the top and the bottom, I knew the color scheme. I knew what was supposed to go here. Here I don't. It's all black. Does that have any meaning? Is that going to cause any trouble? Well, let's see if it does. But in any case, I pick a side, and I see that, well, this white one belongs here. I need to put an orange one here. Is it this orange one, or is it this orange one? You actually don't know. And if you don't know, maybe there's a potential for what I would call false equivocation. I'm saying that these two are the same. It could be this that belongs here, it could be this. Could that be a problem with the solution that might be a little more complex? Well, let's find out. So let's say it's this one. Move it to the side, double turn this down, bring it in, turn it up. This edge is in, this edge is in. Now what about this one? Well, we can put this one in or this one in. Which one? Your choice. I'll do this guy and turn. Okay, so now I've got the edges of this layer. I just need to put the corners. So I'm going to put this down on the downside here, looking for blue and orange. Is it even up here? It's not, which means it's down here, so we'll keep going. How about orange and white? Here's an orange and white. Is it the one that belongs? It does not. Actually, it does, because this orange will come to here, this white will come to here. When you switch this, when you move this down here, it actually flip-flops. So we do the same thing. 2R, U, 2R, UI, 2R. So this is in. We've got the same expected placement, misplacement over here. So I keep it in this position and move on to the next one. White and blue. Here's a white and blue, but this does not belong because it'll flip-flop, which means the blue will be here. Find another white and blue, this one. 2R, U, 2R, UI, 2R. So now that's in, and all is right with the world with the middle. What about this guy? Well, I need a blue and orange. You can see this is the wrong blue and orange, so we need to put this one in. But if we do that, we're going to end up with misplacement, so we're going to do the same technique we did with this guy. Just move this to the side, and I'll put a dummy one in. 2R, U, 2R, UI, 2R. All right, now that I got the dummy one in, we find our real blue and white. It's blue and orange, rather. It's not this one, because this will flip. It's this one. 2R, U, 2R, UI, 2R. And you can see now these two are done. So with this layer, we're going to do the same thing. Now, here's a problem. The problem is I've got these two that have to be flip-flopped. And I know, based on the law of cubes, which states that you can't do an odd number of swaps, you can only do an even number of swaps, this isn't going to work. By odd number of swaps, we're swapping these two, it's one swap. So that's what I mean by odd number, one swap. You can only do even number, which means one swap, two swaps, like a 3-cycle or variations of that. So this could be considered potentially a parity, right? A parity because I can't do that. I would have never come up with this configuration in this puzzle. I wouldn't have come up with it because the colors would have guided me. I don't have the colors to guide me, but I would never have a situation where just these two would happen. I had a hard enough time trying to get it to where the top didn't just solve itself. But in any case, this isn't really parity by what I would call parity. This is false equivocation because I had warned you that we had an option of doing two types of pieces in this position. And we just falsely equivocated one for another when it was truly one piece that belonged. So what this means is we don't really like one of these colors here. So all I'm going to do is I'm going to swap one of these colors, this color for this. And the way that I'm going to do that is I'm simply going to take this, move it up here, move it in, move it down. Now it took these out, But now I know that this, quote, parity situation, this false equivocation is out, and now I can solve it better. And it's a pretty quick reconfiguration here. So this comes to here, 2r u, 2r ui, 2r. And now we move the one that's supposed to be here, which happens to be this guy, 2r u, 2r ui, 2r. So now you can see we have all of these, we've got this layer done. So we're going to follow the same suit with this guy, and you can see all of the issues of equivocation is gone. What I need to do is I need to rotate this in a clockwise manner. So to do that, I'll just do my previous corner swapping algorithm, as opposed to corner switching algorithm, which will only have effects in this puzzle on the edges. 2r u, 2r ui, 2r ui d, 2r ui, 2r u, 2r, and so now we have these two layers done, and if it were this puzzle, you'd be home by now. So now what we do is we just apply the same thing. This whole thing becomes the center, and we just do the same thing. Now, the only other snafu is we don't really know what color is supposed to be on top or on bottom. I don't have the center like I did over here. So the way to decide that, the way to discern that, is we just take a look and see which one matches. So you can see that this color matches this over here, this one doesn't. So this is supposed to be blue. Purple rather. Knowing that it's purple, I'm going to put the purple edges in. So this purple edge is in here. I'm looking for the blue purple edge, rather the white purple edge. Move this down, this whole thing down, this moves up, this moves in. And I'll do the same thing with this. Move this down, put the blue and purple one in, and move it up. And now it's the same technique. I'm going to come across here, and this is going to come down to this side here. 2r u, 2r ui, 2r. This is in, creating misplacement across this whole area, but we don't care about that because we know what to do. Move this in place. I'm looking for a blue and white. Here's the white, here's the here's a blue, here's a white over here. 2r u, boy, this thing loves to turn. 2r ui, just not the way I wanted to. 2r. So now this is good. So now I got to put this guy in, but as you know, I have to put a dummy one in first, because if I don't put a dummy one in first, it's going to cause misplacement here. 2r u, 2r ui, 2r. There's the big dummy. And now we're going to put this one in. 2r u, 2r ui, 2r. Okay, so this is good. Now we just have to do the same song and dance with this. Another clockwise rotation will bring this to here. 2r u, 2r ui, 2r ui d, 2r ui, 2r u, 2r. Move this back, and done. So it was a neat way of adding a bit of complexity to an otherwise easy puzzle. And that complexity is by throwing in some false equivocation, making certain pieces appear the same. So if you tried to apply this strategy, or this strategy rather, to this puzzle, you'd run into that little problem. The recognition of where that problem came from made the solution pretty straightforward, and also bearing in mind that you don't have centers to guide you here. So that's the 3-layer version, that's the 5-layer version. What if we built the complexity even more? In other words, we went from a normal standard version to a crazy version, or a circle version. What happens if we add circles, which separates out these pieces as their own trouble? So how do we go from there? That will be talked about next time.